So we already know that P will be equal to NP. For instance, if SAT was shown to be in P, then all of P is equal to NP. All of NP is equal to P. So for sure, if P is not equal to NP, then SAT and other NP complete problems like clique, three colorability, all of them are not in P. So then the question is this. So now let's take, so suppose P is not equal to NP, right? So now let me draw a Venn diagram. Suppose this is NP, okay? And suppose this is P, the part that I'm shading in blue. Suppose this is P, okay? This blue shaded part is in P. Now, is it the case that so suppose this is NP complete. So maybe I'll just write NPC, sorry. Maybe I'll just write NPC. So NP is this whole thing. This whole, the entire thing, the big circle here is NP. Right? So now suppose this is NP complete. So this green shaded part is NP complete. The question is, are there, so we know that the NP complete languages are certainly not in P if P is not equal to NP. So what I want to ask is, are there languages in the middle or in the intermediate region? So like in the light blue shaded region, is this region empty, or are there languages that are in the intermediate zone, right? So this part is called, so NP is this whole thing, and this middle part I am calling it NP intermediate, okay? So given that P is not equal to NP, we know that P and NP complete are disjoint. Now, does NP constitute of only P and NP complete, or is there an intermediate zone? That is the question. So is the light blue region in the middle? Are there languages there, or are they empty? This is the question. So is there in other words, is there an NP complete language? Sorry, is there a language that is not NP complete, that is in NP but not in P? So in other words, is there a language that is in NP but not NP complete and not in P? That is exactly what is called NP intermediate. Are there NP intermediate languages provided P is not equal to NP? This is the question that is answered by Ladner's theorem. So what Ladner's theorem says is that if P is not equal to NP, yes, there are NP intermediate languages. There are languages that are neither in NP complete nor in P, right? So I'll just give you a very brief high level idea, because the proof is a bit technical, and the techniques used are diagonalization mainly, and we have seen already time hierarchy and space hierarchy where we use diagonalization, okay? So I believe we could just, so I'll just give you a high level picture of this proof, and there is another trick used in this proof. That trick I will explain in a bit more detail, okay? So that trick is called padding, okay? So what is SAT? Okay, SAT is an NP complete language, right, where you're given a Boolean formula, you have to decide whether it's satisfiable or not. Now suppose I write phi is a SAT instance, okay? And to write phi, I require this much, the formula takes this much length, okay? And usually in our usual terminology, n is the length of the input. And what we know is that n, there is no polynomial time algorithm in the length of the input. So if this is the input length, right, let us call it n, then there is no polynomial time algorithm in n, right? So there is no n power k time algorithm for any constant k. Now what I can do is to do something like this. I could take a special symbol, or I can even do it with some ones and zeros, right? Maybe I can make a new special symbol, let's say hash, right? And I can add a lot of hashes. Maybe I'll just write hash star. Okay, so the first part is exactly the same, right? N of length n, which is the same formula phi, and the hash, I'll just change the hash to red color so that you know the distinction. So I'll just make it long, just to, the blue part is just the formula phi, and now there is a red part that is attached to the blue part, right? And now the whole length, right, the length of this whole thing, let us say this is n prime, okay, right? Now n prime is significantly bigger than n, right, because we added a lot of hashes to the end. So in this picture it looks like maybe slightly more than 2 times bigger than n, but think of n prime being much bigger than n. Okay, so think of n prime being, let's say you can add much more, not even a constant time. Maybe n prime could be exponentially longer than n, right? So in that case, now if I have to decide on whether, so there is a Boolean formula here, phi, followed by a bunch of hashes. Now I have to decide if phi is satisfiable. But now the problem length has grown so big. So the running time to decide this, so if the running time of deciding SAT, let's say there is an exponential time algorithm by trying out all the possible assignments, right? So here also we can do that, but now that requires 2 power n time. But when you measure the time as a, so suppose n prime is, let's say 2 power n, right? So now what happens, suppose if n prime is 2 power n length, now an algorithm that runs in 2 power n time is linear in this, right? So an algorithm that runs in order 2 power n time is now a linear time algorithm, right? It is just constant multiplied by input length, because the input length is now so much bigger than it is actually it's actually 2 power n, right? So, or it is constant times n prime, right? So what I'm saying is that if n prime is sufficiently long, then now it is a linear time algorithm. Linear time means linear time is obviously polynomial time, right? Because it's just a linear factor. So by adding enough of these hashes, now we can bring down the complexity of the problem, because the complexity is measured in terms of the input length, and by blowing up the input length, while not really increasing the problem size itself, right? The actual problem is still only n size, right? So by blowing up the input length, but keeping the inherent problem size the same, but the actual representation length, by blowing that up, we are now when measured as a function of the input length, the problem becomes now linear time or polynomial time, right? So this is what is padding. So by adding padding is just about artificially increasing the length of the input, so that when measured as a function of the input length, the problem now becomes easier, right? So from exponential time, now we went to linear time, which is polynomial time as well. So this is padding. So you saw how to go from exponential to linear time. Now the same trick is used in the proof of Ladner's theorem as well, right? So it takes SAT and adds a bunch of hashes to the end of SAT and tries to make it easy, right? So the assumption, again, the starting assumption is that P is not equal to NP. So SAT cannot be solved in polynomial time, right? So SAT requires more than polynomial time, right? It could be exponential or sub-exponential, something less than exponential also, but certainly not polynomial time. So now we want to pad SAT by enough number of hashes so that it no longer is NP complete. The complexity comes down from the NP completeness. But we do not want to pad it so much that it becomes polynomial time. So here we padded it so much so that it became linear time. So that is something we do not want. We just want to make it not NP complete, but we also do not want to do it so much that it becomes comes down to P, right? And so that is a challenge. So you want to exit this green area, but do not want to fall into the bottom dark blue area, but want to remain somewhere in the middle light blue area, right? So starting from SAT, we have to pad it enough so that it falls in the middle light blue area, and this is what is the proof. The proof is all about. So it figures out how much exactly to pad by, so that it comes out of NP complete, but does not fall into P. That is the idea of the proof, and it uses diagonalization as well, amongst other things, right? So the diagonalization is used to show that it is not in P, right? So I'll just give you some candidate problems which as of now we do not know whether they are in P, and we also do not know that are not NP complete. So most people believe that P is not equal to NP. So people think that these are problems that are candidates to be the NP intermediate problems, right? So I'll explain the two problems. One is graph isomorphism. So what is isomorphism? Isomorphism is saying that these two are the same graph. So it is just two graphs, and whether these two graphs are the same. So that is a bit abstract. So I have an example. So I have three graphs here, right? The blue, the red, and the black. In fact, they are all the same graph. They are all isomorphic to each other. So let's see why they are isomorphic to each other. So I will again, I have not practiced this, so you can see the complexity involved. Right? So let me just label the blue graph 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So isomorphism means that the second graph, when we say that the blue and the red graph are isomorphic, it means that the second and third graphs, the blue and the red graphs are the same graph except for some rearrangement of the vertices and renaming, right? So here I am giving it in a pictorial sense. When you're giving it to a Turing machine, you may give the adjacency matrix or the adjacency list. So the matrix or the list, the order of the vertices may have been jumbled up. But just to make you understand, I'm just drawing a pictorial version of graph isomorphism, right? So let us see. So 1, 2, 3, 4, 5 form a 5 cycle. So here we have to find a 5 cycle. So maybe why not this? So I will try to, the claim is that, let's say 1, 2, 3, 4, 5. So these form a 5 cycle because let me try to outline, right? This form a 5 cycle, and the remaining vertices also form a 5 cycle, but then I have to be careful because one is adjacent to, in the blue graph, one is adjacent to 2, 5 and 6. So in the red graph, it should also be adjacent to 2, 5 and 6. It's already adjacent to 2 and 5. Now it should be also adjacent to 6. So which makes this vertex 6. Similarly, 2 is adjacent to 1, 3 and 7. It's already adjacent to 1 and 3. So this should be 7. 3 is adjacent to 8. Similarly, so this should be 8. 4 is adjacent to 9. So this should be 9, and the central vertex should be 10, adjacent to 5. So let's see how the inner, in the blue graph, how the inner star is connected. 6 is, so maybe I'll just write down here. In the inner star is 6, 8, 10, 7, 9 and back to 6, right? So let's see whether the same thing is true here. 6, 8, 10, 7, 9 and back to 6. So indeed it matches. So this is why it's an isomorphism. So it is the same graph but just redrawn in a different way. And in fact even this graph is a redrawing of the same graph in a different way. These two are both the same graph, the red and blue. What I'm saying is that the black graph in the right side, that's also another isomorphic graph, right? So that is a problem of graph isomorphism. Given two graphs, we have to decide whether they are the same. By rearranging the vertices, can we get one from the other, right? One from the other means the edges should be the same. So here 1 is adjacent to 6, 2 and 5. That is the same in the blue graph as well as the red graph, right? And there are evidences. So this is, we do not know a polynomial time algorithm for graph isomorphism, and there are strong evidences, meaning there are some results that indicate that this is not NP complete. Meaning, if this is shown to be NP complete, something else happens which is unlikely. Okay, so I do not want to get into that, but the point is that it is believed to be a problem that is not NP complete. Also, we do not know a polynomial time algorithm. So that is why people think this is an NP intermediate language. Another problem that is believed to be NP intermediate is factoring, right? So factoring is the problem of given a number, just to factor the number into prime factors. So that is this is not a decision version of the problem, but a decision version. There are maybe more than one way to write a decision version. One of such a way to write a decision version is to write like this: n comma k, where capital N has a prime factor that is at most k. So in other words, we are asking, does number n have a prime factor smaller than k? So for instance, sorry, I'll use another color, or maybe I'll use another color. So for instance, 51, 10, this is a yes instance because 51 has 3 as a prime factor, which is less than 10. At the same time, 101, 10 is a no instance because 101 is a prime number, so it does not have a prime factor smaller than 10. In fact, it does not have a prime factor smaller than 100 itself, right? And even this is a no instance, 121, 10, right? Because 121 is simply 11 squared, so it does, the smallest prime factor is 11, so it does not have a prime factor of size 10. Anyway, the goal is, you can certainly solve this, decide this in polynomial time if you can factor in polynomial time, but we do not know how to factor in polynomial time. So this is also a problem in NP, but we do not know whether it is, we do not know a polynomial time algorithm. Also, it is not believed to be NP complete. And maybe I'll just say the same thing for graph isomorphism also. Given, so it is, the graph isomorphism is also in NP. Given a mapping, it's easy to verify. If I tell you, you put 1 to 7, 2 to 8 and such things, like between the two graphs, if I say in G1 1 you can map it to G2 6 and so on, then you can verify that they are the same graph. But so it is an NP, but there is no known polynomial time algorithm, and also it is believed to be not NP complete. Same thing for factoring. So that is about NP intermediate languages and Ladner's theorem, which simply states that if P is not equal to NP, there are NP intermediate languages.
Swayam Prabha, Digital India, Educated India.
Hello and welcome to lecture 23 of the course Computational Complexity. In this lecture, we will see Oracle Turing machines, right? So we have seen reductions and Oracle Turing, which are many to one reductions, many one reductions. Oracle Turing machines are another way to view reductions using what is called an oracle. Okay, so if you Google for the word oracle, right? Obviously there is this software company called Oracle Corporation, but if you for the English meaning of the word oracle, so this oracles were people who were in like some in ancient times or mythologies or whatever, people who used to be maybe in a maybe in the courts of kings or maybe otherwise, who used to provide kind of advice supposedly from the gods or from the future or somewhat prophecy type of things, right? I've pasted a snippet of the Wikipedia entry for the word oracle. So they are people, so oracles were people who were consulted in order to get like advice, right? So this is keeping this in mind, let's try to understand the word what are Oracle Turing machines, right? So Oracle Turing machines are Turing machines which have access to an oracle. What are oracles? So oracles could be so we will first define oracle as a specific problem or specific language. So it could be for instance, I think in this lecture mostly we will use the SAT oracle. Okay, so we know that SAT is an NP complete language. So a SAT oracle, if you write down a SAT instance, if you write down a Boolean formula, the oracle will immediately tell you whether this formula is satisfiable or not. So this is what the oracle does, right? So you get the yes or no answer immediately and the correct answer. So it's not just any yes or no answer, right? So an Oracle Turing machine has the functionality or has a way to ask the oracle queries and get responses, and can use these responses in its computation. Right, so it can make the SAT query many times if it has a SAT oracle. It need not be a SAT oracle. It could be any oracle, right? So it could be a three-colorable oracle, right? So whenever you give it a graph, it immediately tells you whether the graph is three-colorable or not. So the oracle is it's an oracle, right? So it doesn't take any time. You give it, it immediately gives you the answer back. Yeah, so you give the question, it immediately gives the answer back. It doesn't take any time. It is just one step. So how is it how is it formalized in this notion? So it's a Turing machine, right? And it has a special tape called the oracle tape or the query tape, right? And on the query tape, the Turing machine will write queries. Right? So queries, it need not write in one step. It could be constructed in a sequence of many steps. But and so if it's a SAT oracle, it will write a SAT instance. So when the SAT instance or the query is ready, at some point it will go to a special state. The special state being the Q query. Right. This is the first one is Q query denoted by Q with a question mark in subscript. Some textbooks may say Q query. And then the next step, the oracle gives the response. How does the oracle give the response? It will look at the query tape or the oracle tape. So it doesn't need time to read or anything. It's just one step. And then it will immediately move the Turing machine to the yes state or the no state. So this yes state and the no state are also special states. So all of these three are special states: Q query, Q yes, and Q no. So if it is a yes instance, it will move to Q yes. If it's a no instance, it will move to Q no. Right. So this is what it does. Right. And an Oracle Turing machine is a Turing machine with these properties. Right. And the oracle could be any language. Like as I said, it could be SAT, it could be three-colorable, it could be subset sum, it could be like two-colorable, anything, right? So depending on how powerful the language that corresponds to the oracle is, you'll find different we'll find different results, right? So how does it function? I've already described, but I will just go through it again. The oracle is the oracle corresponds to some language. So here we are denoting that language as A, right? So it has access to the A oracle, right? The language A oracle. So in what I described, the oracles possible are like, it could be like I said, SAT or three colorable. Any language can be used as an oracle, right? And at some point the string is written on the query tape or the oracle tape. Maybe I'll just try to. So there are Turing machine tapes. Let's say this is the work tapes. Let's say these two are the work tapes, and let's say the black one is the oracle tape, right? So this is the oracle tape. The other ones are work tapes or the query tape. So it will keep filling up the oracle tape, and then it will move to a state, the oracle state Q query or the query state, and then depending on what is there on the oracle tape, it will move to Q yes or Q no. So if it's a yes instance, it will move to Q yes. Right? This is what basically the oracle will check whether the string is a part of A or not a part of A. This is what happens. And such an oracle is called, or such a Turing machine is called, if a Turing machine M is there with access to an oracle A, it is denoted by M with superscript A. So it has M and it has access to the oracle A. And we will see later, we will see generalizations of this, where we will see complexity classes with access to an oracle. Okay, so we'll define what they are. We'll soon see, and we can even define, again, this we will not quite do, but we can do that. If you see textbooks, you may see this notation where complexity classes have complexity classes as oracles, right? So where both the subscript as well as the superscript are both complexity classes, right? So let me just define the first one. C1 with access to A means, so it's a complexity class. So first we'll use P superscript A to define it. So basically you have a deterministic polynomial time Turing machine, right? So what is P? P is a collection of languages decidable by deterministic polynomial time Turing machines, right? But now P superscript A means it is the class of languages decided by deterministic polynomial type Turing machines. That's exactly what it was for P, but with access to an A oracle, right? But with the access to an A oracle. So this red underlined part was not there for P. So that is the access to the oracle. NP superscript A is again the same thing. So what is NP? NP is a class of languages decidable by non-deterministic polynomial time Turing machines. NP superscript A is the class of languages that are decidable by non-deterministic polynomial time Turing machines with access to an oracle A. Right? So again, the red underlined part at the end of the sentence is what changes. Right? So this is what a complexity class superscript A means. It is the same machines that form part of that complexity class, but with access to an oracle A. C1 superscript C2 will not define now, just to avoid making too many definitions, right? Okay, this is the notation. So what is the reason for making this definition, or what is the motivation behind this? So we have seen many one reductions, right? Which is denoted A less than or equal to subscript MB, right? So although we didn't define it in this course, you must have seen it in the theory of computation course that in your undergrad. But the same principle applies for the polynomial time and log space reductions, both of which we saw in this course, right? So what was the principle there? So the principle was that W is in A if and only if f of W is in B. So basically we are transforming an instance of A into an instance of B. So you're transforming A instance W to a B instance F of W, and then using that to solve A. So basically converting A instance to B instance and then using an algorithm of B to solve A. Correct? This is what we did in the many-one reductions or polynomial time or log space reduction. So many-one reductions is just the same thing, except that there is no restriction on the time or space used by the machine. But polynomial time and log space are specific cases of many-one reductions. So Turing reductions, right, which is what we are going to define now, or there is one issue, or there is one specific limitation with the many-one reductions or log space or polynomial time reduction. So basically you convert the problem instance and then use the decider for B to decide A. So this can be viewed as asking the decider of B just once, right? So you just convert it and then ask the decider for B, is it in B or not? Is the converted instance in B or not? So basically we are getting only one query to ask the B decider. So why not ask the B decider many times? Do we get any advantage out of that? Do we get any benefit by allowing us the greater possibilities of asking B many times? So that is what Turing reduction does. So Turing reduction is basically an access to an oracle of B. So when you have an access to an oracle, you could ask queries to the oracle multiple times, not only once, right? So the question here with many-one reductions was, why can't we query B multiple times, right? And that is what is addressed by the Turing reduction. So basically we say A Turing reduces to B if A is decided by a Turing machine M with access to an oracle B, a B oracle, right? So we'll see one simple example. So one is which is very, very simple, and maybe you might feel it is silly, but even this simple or silly example illustrates the power of Turing reduction over many-one reductions, right? So the simple example is that SAT complement is reducible to SAT using Turing reduction. So subscript or less than or equal to subscript T indicates Turing reduction. SAT complement is reducible to SAT. So what does it mean? It means that there is a machine with access to a SAT oracle that can decide SAT complement. So given a SAT complement instance, right? So let's say given a formula phi, it is in SAT complement if it is not satisfiable, or in other words, if it is not satisfiable, it is in SAT complement, which means it's a yes instance of SAT complement, right? So which means it's a no instance of SAT. So basically all that we do is we ask phi to the SAT oracle. If the SAT oracle says that it is a yes instance, you answer no, and if the SAT oracle says it's a no instance, you answer yes. So which is what is written here. If the SAT oracle accepts, you reject, and if it rejects, you accept. So basically you flip the output of the SAT oracle. So you start with an input, you just write down the input in the query tape, ask the SAT oracle one query and flip the output, right? So what we have shown here is, if this is a machine M that does this, we have shown that SAT complement is decided by, okay, maybe that's small, is the language of this machine M with access to SAT oracle. And if you notice, all that M is doing is just writing down the input in the query tape, which can be done in linear time, and then flipping the output, right? So this is certainly linear time. So M is a polynomial time machine, a deterministic polynomial time machine. So I can as well say that. So we can as well say that SAT complement is in. SAT complement is in P superscript SAT. It is in P with access to a SAT oracle, right? Because M is a polynomial time, deterministic polynomial time machine. In fact, it's not very difficult to see that even SAT, maybe I'll write it above. It's not very difficult to see that even SAT is in deterministic polynomial time with access to SAT oracle, right? Because it's trivial. Because you want to solve SAT and you have access to the SAT oracle, then all the machine has to do is just copy into the query tape and make the query, and then accept or reject accordingly. The same thing without flipping. And in fact, now SAT is a NP complete language. SAT complement is a co-NP complete language, and we have seen that using Turing reduction, you can reduce a co-NP complete language to an NP complete language, which was not possible if we just used polynomial time reductions as we had learnt. Right? So you see that Turing reduction is actually more powerful. Even though this particular example was extremely simple, you see that even the simple example illustrates this fact. Right? So SAT is an NP complete language and SAT complement is a co-NP complete language. So in fact, both of them are contained in P superscript SAT, which means that the entire class NP is contained in P superscript SAT, P with access to SAT oracle, because SAT is contained in P superscript SAT. Right? Because you could take any NP instance, you can reduce it to a SAT instance and then ask and SAT is in P superscript SAT. And co-NP, likewise, you can reduce it to a SAT complement instance, and even that has been shown to be in P superscript SAT. So both NP and co-NP are in P with access to a SAT oracle. And notice that P with access to a SAT complement oracle is the same thing, because if you get yes no answer, a SAT complement will tell you whether it is not satisfiable or satisfiable. It's the same thing that SAT oracle also tells you, just that it answers the flipped output. Right? So you take the answer of the SAT oracle and flip it, you get the SAT complement oracle. Right? So P superscript SAT, which is equal to P superscript SAT complement. So NP and co-NP are both contained in that. Right? Maybe two exercises. The first exercise is to kind of see how, or for you to see how powerful is this idea of making multiple queries to a certain oracle can be. Right? Suppose you have a SAT oracle, right, which tells you yes or no given a SAT instance, whether it is satisfiable or not. Now please construct an algorithm which, given a Boolean formula, if it is not satisfiable, then you just output it's not satisfiable. If it is satisfiable, then actually the algorithm should provide and should output an assignment, a satisfying assignment for the formula. So if given phi, it should tell, if phi is satisfiable, it should tell a satisfying assignment for the formula phi. Right? So try to construct this using a SAT oracle, and you will need, and what I am telling you right now is that you will need to make multiple calls to the SAT oracle, multiple queries to the SAT oracle, but still you can find it. And the idea used in this is very, it's not that difficult to find, but if you think hard, you can find it. And the idea used in this will be useful for a theorem that we will see later in the course, right? So this, the idea used here, maybe I'll just tell the name of the idea. It's called self-reducibility. Okay, but anyway, you don't need to know what self-reducibility is, etc., to answer this exercise. Just try to see. So maybe what the first step is, let's say you given a formula phi, you just give phi to the sat oracle. So sat oracle will say whether it's satisfiable or not. If it is not satisfiable, you are done, right? Because there is nothing to be done. If it is not satisfiable, there is no satisfying assignment. If it is not satisfiable, you are done. If it is satisfiable, then you have the task of producing a satisfying assignment. Think how you will go about this, right? So remember, the SAT oracle can take any formula, any instance of satisfiability as an input. So what instances can we give? Think about this. Next exercise is to show that if A is in P, okay, if A is in P, then the class P with access to an A oracle is P itself. Okay, so we saw that P with NP is contained in P with access to a SAT oracle. NP and co-NP are both contained. But however, that was for SAT. If A is in P, right, then P with access to an A oracle is actually P itself. So obviously P is contained in this direction is easy, right? P is contained in P with access to an A oracle, right? So usually, just again, this is one of these things I'll just say. Whenever you have to show that two sets are equal, two classes here in this case are equal, one of the standard ways to go about doing this is to show that the left hand side is a subset of the right hand side and the right hand side is a subset of the left hand side. So in this case, P is obviously contained in P with access to an A oracle, right? Because P is, well, P itself. So even without accessing the A oracle, we can say P is this. So A oracle only adds more power, right? But the other direction, P with access to A oracle, we have to show that it is contained in P. This will be, again, this is not very difficult to see because A itself is in P. A is also a polynomial time. A is also decidable in polynomial time. So instead of asking the oracle, this machine itself can run the algorithm for A. So that is why the other direction, P with access to A oracle is contained in P. That's how that comes about. That is a slightly that will require a bit of explanation, but the other one is even easier, right? And yeah, that's what I want to say in this mini lecture. Just defined oracle Turing machine, which is a special type of Turing machine which allows us to ask an oracle some queries, right? And I defined M superscript A as a machine M with access to an oracle A, and P with superscript A is the complexity class, machines in complexity class P with access to an oracle A. Likewise, NP superscript A, we define Turing reductions as instead of reducing it to that language, you can have oracle access to that language, right? So Turing reduction is A Turing reduced to B if there is an oracle Turing machine M such that A is the language of M with access to oracle B. And finally, some simple inferences using for these complexity classes and the exercises. And that's all I have for lecture 23. Thank you.
Hello friends. The urge to communicate is as old as time. Man, being a social animal, needs to reach out to other people and let them know how he feels, what he thinks. He needs to express himself. To fulfill this need, man has developed various arts like singing, dancing, creating shapes and many more. Painting is one such art which has existed since the earliest cave paintings of prehistoric man some 30,000 years ago. Since then, this art has undergone various developments. Several styles of painting have evolved over the years which are peculiar to the regions they originate in, depicting their culture and ideology. One such special form of painting is the tanka. This form of art comes from the roof of the world, Tibet. This land of snow has been greatly influenced by the art and culture of its neighboring regions like Kashmir, Bihar, Orissa, Bengal in India, Nepal and China. Taking artistic inspiration from them, Tibet created a remarkably expressive style of painting. Tibetan paintings fall into three major categories: wall frescoes, adornments to printed text, and tankas or scroll paintings. Some tankas are decorative in nature in the sense of celebratory and inspirational. Vajrabhairav is supposed to destroy inner hindrances in the path of enlightenment. Vaisravana enriches wealth and religious experiences. The balance of the world is protected by goddess Maksorma and Chintamani Mahakala, and Yama protects the practitioners from inner distractions. Tankas are also meditational in nature, depicting meditation deities like Samatara, the blue-green savior goddess, Kalachakra, Kurula, and many others. Apart from their religious content, many tankas are of great historical and artistic value, as they depict monasteries built by the various Dalai Lamas over the years. These monasteries were later destroyed in the Cultural Revolution of 1966. An entire series of tanka paintings depict legends from the life of Buddha. The Buddha seated on the lotus throne takes the central position. Indian influence is evident in tankas that portray Jatak malas, that is, previous incarnations which were written by Aryasur. Incarnations of famous Indian and Tibetan teachers find an important place in these tankas. Tankas tell us a lot about Buddhist culture and beliefs. Hands folded in the gesture of meditation